You've probably seen this in earlier classes in a simple situation, such as the following. I'll have an object, and I'm going to move it along a straight line a certain distance. This motion is going to be caused by a force that points in the same direction that the object is moving, and the strength of the force is a constant. It doesn't change from point to point. You can use whatever systems of measurement you like. For instance, you might use pounds for the force and feet for the distance. The unit of work that corresponds to that choice is foot-pounds. Or you could use metric units. You could use newtons for the force and meters for the distance. The Newton meter is also known as the joule. These are also units of energy, so we'll think of energy and work as basically being the same word. The kind of elementary calculations that you do in prior classes are things of the type: you have a 50-pound object sitting on the ground and you lift it straight up 10 feet, so the force is the 50 and the distance is the 10. Obviously, the amount of work done is going to be 50 times 10. That is to say 500 foot-pounds. As we're going to see a little bit later, this is not exactly right, because as you move away from the surface of the Earth, the force due to gravity actually decreases, but this is an excellent approximation which is useful in many ideas. This is an excellent approximation that's useful in many situations. The situation that I want to talk about in this video has to do with Hooke's law. Hooke's law says if you have a spring, it has a certain natural length which corresponds to not putting any force on the spring. I'm going to call x the displacement of the spring from its natural length. If I haven't put any weight on the spring, that corresponds to x equals 0. I'm going to think about attaching a weight to the bottom of the spring and having it stretch the spring a certain amount. In this early way of thinking, I'm going to start with displacement 0, and I'm going to end at x equal b. Hooke's law says that the force that I'm going to need to do this is a constant times the displacement from the natural position. In terms of letters, I can write this in a kind of shorthand. F is going to be k times x. This is called Hooke's law. First, we need to understand what this means exactly. So I'll think of a specific example. F is going to be 3 times x. I'll think of my x as being in feet and my F as being in pounds. My spring has some natural length associated with it, which I'll call x equals 0. If I wanted to attach a weight to the end of the spring so that I stretch the spring 1 foot, the weight would need to be 3 times 1, 3 pounds. If I wanted to stretch the spring more than this, I would have had to attach a heavier weight. The total displacement now will be x equal 2 feet. The amount of force that I'm going to need is F equals 3 times x, 3 times 2. The force needed to do this will be 6 pounds. And likewise, if I wanted to stretch the spring 3 feet from its natural position, the force at the end, the weight that I'm going to have to attach to make that happen, is going to be F equals 3 times x, 3 times 3, which is 9 pounds. It's important to understand that if I wanted to stretch the spring to x equal 2, I'm going to have to stretch it to x equal 1 first, and then stretch it some more. The force experienced during each of these periods of stretching are going to be different because the x's are different. Likewise, when I want to make x equal 3, if the spring starts off in its natural length, I'm going to have to start pulling downwards. Eventually x will be 1, x will continue until it's 2, and then eventually x will be 3. When I stretch the spring to this length, the spring will have experienced a position, everything from here to x equals 0, and everything from here to x equals 0 as well. The force is constantly changing for these different x values, so the idea that I'm just going to take force times distance in order to get work, that can't work here because the force isn't a constant. So the question of how much work is done by stretching this spring 3 feet is not as easy to calculate as you might think that it is. The idea is going to be the same as we've done before. I'm going to think of starting at x equals 0 and then increasing x by a small amount. For purpose of illustration, my small amounts will all be 1/2. So x will have increased by 1/2. I'm going to pretend that this is such a fine step that the force doesn't have a whole lot of change in it when I change from x equal to 0 to x equal to 1/2. I'm going to approximate this non-changing force value by the force at x equal 1/2. To make this a little bit more suggestive, I'm going to write the force literally as k times x, 3 times the representative x value, which in our previous work we've been calling c number I, and 1/2 minus 0 is how much x changed on this first little piece of the situation, so I'll call that the change in x number 1. I'm going to think of what happens after that. So I've already done the work needed to stretch the spring to x equal 1/2. I want to increase the x some more. This new addition changes the x from 1/2 to 1, so the change in x in the second bit is also going to be 1/2. I'll call that delta x number 2. The interval from 0 to 1/2 is not the same interval as 1/2 to 1. The force I'm still going to pretend is more or less a constant and has the value at the biggest x, just as we did before. The amount of work associated with this chunk is going to be 3 times delta x number 2. F of 1 is the force that the spring is experiencing at x equal 1. This amount of work, if you notice, is different from the amount of work from chunk number 1. This is because on chunk 1, where the x was smaller, the force was smaller. In a similar way, I'll think of increasing the x 1/2 foot at a time, approximating the force on each piece by the force at the end, and I can calculate the contributions to the work that comes from the third subinterval, the fourth one, the fifth one, and the sixth one. All of the delta x here's are 1/2 foot to be exact. Since I've chosen all of the delta x's to be 1/2, I can factor a 1/2 out of that to simplify my calculation. If I've done my typing on the calculator correctly, this is 15.75. This is work. I'm measuring my forces in pounds and my distances in feet, so this is 15.75 foot-pounds. In view of what we've been doing in this entire chapter, the observant will notice that I'm adding up a bunch of stuff. I'm adding up some quantity evaluated at a representative x value multiplied by a delta x number. I get an approximation to the thing that I'm interested in by doing that. If I want to make the approximation perfect, we're going to let all of the delta xi's tend to 0, which consequently means the number of terms will have to become indefinitely large. This will turn this into an integral. If an object experiences a force F, which may vary from position to position, starting at x equal A, ending at x equal B, and I want to know how much work is done by a force that points in a parallel direction from A to B, what I'll do is this. Once again, we'll chop the range of x values up into a number of smaller ones. I'll look at one of them whose width is delta x number I. Within each subinterval, I'll pick a representative value, x equals ci, and I'm going to pretend that the subinterval is so small that the force as a position function of x doesn't have much opportunity to change on that subinterval. I'll approximate the force over the entire subinterval as being F evaluated at ci. I now have a constant force, more or less, traveling an object a distance of delta x number I. The amount of work associated with that small piece of the proceedings is given by force times distance. Having done this 1,000,003 times by now, we know what we're going to do. We're going to add up all of those contributions, then we take the limit as all of the delta xi's tend to 0, which turns this into an integral, and we will have our work calculation as an integral problem instead. To get work, all we have to do is integrate the force with respect to displacement from the starting value of the displacement to the ending value. If we return to the spring situation that we were looking at, the force was F equals 3 times x. We started at the spring's natural length, where x is 0, and we stretched the spring 3 feet. So f of x is 3x, a is 0, b is 3. In preceding work, we've just shown that the thing that I have to calculate to figure out how much energy or work is needed to stretch the spring from 0 to 3 is just this integral. Doing the routine antiderivative and substitution business, I find out that the amount of work is 13.5 foot-pounds. If you'll remember, we approximated this with a Riemann sum, a finite number of terms. Our rough approximation to the amount of work was 15.75 foot-pounds, which is not tremendously different from the exact value, 13.5 foot-pounds. This is going to be our general strategy. If I have a formula for the force, and I know an initial and ending position, then I'm going to integrate from initial position to ending position, force as a function of x, integrated with respect to x. A typical problem this type is you have a force of 50 pounds, it stretches a spring 4 feet from its natural length, and you want to calculate how much work was done. Since in prior classes you learned that work is force times distance, if you read this without thinking about it, you almost want to say 50 times 4, which is 200. But that's wrong. If you start at natural length and slowly start stretching the spring, early on in the proceedings, very little force is needed. It's only at the end that you're having to exert 50 pounds of force. The force isn't constant, so 50 times 4 is automatically wrong. The meaning of this sentence, though, is it tells you how to figure out the spring constant. If you're talking springs, then you're talking Hooke's law. This relates the force needed to stretch a spring a certain amount, and the problem states that F equal 50 goes with X equal 4. What that sentence tells me is, it tells me what the K is. It tells me that K is 12.5. Knowing that, I now know exactly what the force that goes with a given X is. The force in this situation is 12.5 times whatever the displacement from natural position is. Our earlier comments say, this is what I integrate to figure out how much work is done. I've got to integrate the force, 12.5x, with respect to x from the starting x value, which is 0, to the ending x value, 4. The amount of work needed is 100 foot-pounds. This sort of problem is very direct. Sometimes people will play word games to make sure that you're paying attention, so I at least want to look at one of those too. It's very easy to get mixed up. It takes 15 foot-pounds of work to stretch a spring from its natural length, x equals 0, to x equals 5. That's a statement of fact. The question is, how much work is done stretching the spring from x equals 1 to x equals 2? If you go back and look at what we just did, on one level, the question is nothing. You can just write the answer down in a certain sense. I just have to integrate the force, which is k times x for spring problems, with respect to the displacement. And in the question part, the second part, the x goes from 1 to 2. So obviously the amount of work is going to be the integral from 1 to 2 of kx dx. This is easy to integrate except for the fact that I don't know what k is. Somehow the other sentence must tell me what k is. The other sentence doesn't say it takes 15 pounds of force to stretch the spring 5 units from its natural length. It says it takes 15 foot-pounds of work instead. So what does that mean? 15 is equal to the amount of work that it takes to do something. 15 is the amount of work that it takes to stretch the spring from x equals 0 to x equals 5. That is, it's the integral from 0 to 5 of kx dx. This is an equation that is going to tell me what the k is. Once I know what the k is, I can answer the question, because then I'll know the k that I didn't know before. Keeping in mind that k is a constant, I can pull it out of the integral. Antiderivative for x is 1/2 x squared. If you put in x equals 5 and x equals 0, subtract, you find out that this integral is equal to k over 2 times 25. It is equal to 12.5 times k. But on the other hand, this is the work needed to go from x equals 0 to x equals 5, and we were told that that amount of work was 15, so it has to be true that 12.5k and 15 have to be the same number. So 12.5k has to equal 15. K has to be 15 divided by 12.5. K is 1.2. I can start with any x value, end at any other x value. the amount of work is going to be the integral over the relevant range of x values of 1.2x dx, and this is easy to calculate. So a direct calculation tells me the answer to the question part of the problem is the amount of work needed to go from x equal 1 to x equal 2 is 1.8 foot-pounds. I hope this has been clear enough for everyone to follow, and I hope everyone's having a good day. I'll talk to you again soon.